All right, welcome everybody. Today we're going to talk about lesson 14A, and I'm splitting lesson 14 into two parts. Part A today and part B tomorrow. You won't have homework 14 until after you watch part B tomorrow. And these don't really correspond exactly to sections in the book. So I'm just going to call this chapter 2 calc connections. And today we're going to talk more specifically about the idea of continuity and something called the intermediate value theorem, or the IVT for short. I've been talking about continuity for a couple of days now, but we really want to kind of nail down what exactly it means to be continuous. So a function is continuous at some value, let's just say x equals c, if there is no interruption in the graph of f at c. Basically, a continuous graph is unbroken and there are no holes, no jumps, or no gaps. Bottom line, if you can draw the entire graph without having to pick up your pencil, then you would say that the function is continuous. And again, it's continuous at this particular value c. That particular value will change from problem to problem. So we're going to use c in this example to represent anything. Something important to note about chapter 2 from section 2.1 to 2.5, all polynomials are always continuous. Nice, smooth curve. Lines, quadratics, cubics, quartics, all of those are polynomials, which means they are 100% continuous. So what happens if something is not continuous? Well, you don't really use the word discontinuous. What you would say instead is there is a discontinuity. You would not only tell me if there is a discontinuity, you would tell me where it is, and you would tell me what kind. Instead of using random value c for these examples, I'm going to use some random value a. So the first type of discontinuity that you would be expected to recognize and name is something called a removable discontinuity. And a removable discontinuity is basically a hole in the graph. A removable discontinuity, as far as discontinuities go, is considered to be a good one because it's an easy fix. If you take a look at the graph here, at A, there is one single solitary hole in the graph, which means if I wanted to fix it, all I'd have to do is fill it in, and then it would become continuous. So again, we would say there is a removable discontinuity at A. Whether there's a closed circle in the area or not doesn't matter. As long as there's literally just an open circle, that is called a removable discontinuity, and it's located at the x value of A. Just so you're aware, the opposite of being a removable discontinuity is being a non-removable discontinuity. Those are considered to be the bad ones because they don't have an easy fix. And further, they're separated into two categories. So here in B, this is called a jump discontinuity at A, which hopefully makes sense because you literally have to jump from one piece to the other. The third kind of discontinuity is called an infinite discontinuity. That occurs when you have a vertical asymptote, which we can see we have with the dotted vertical line at A. So again, we would say at A, there's an infinite discontinuity because it's going all the way up to positive infinity on this side and down to negative infinity on this side. Hopefully you remember that vertical asymptotes typically come from denominators, but we'll get into the specifics as the chapter goes on. So what would these questions look like? Well, here, identify the location and type of discontinuity, if there is any, then state where the function is continuous. So when I'm asking you for the location, I'm asking you at what x value. So here you can clearly see that at 0, again, x equals 0, there is a break in the graph. You would have to jump from one piece to the other. So we're going to call that a jump discontinuity at x equals 0. Then, based on the picture, there are no other discontinuities, which means it is continuous everywhere except for 0. So you would say that it's continuous from negative infinity to 0, and then from 0 to infinity. Doesn't matter about the open or closed circle in this case. Basically, because the break is at 0, that's why you're going to use parentheses for both. How about this next example here? So if there is a discontinuity, tell me where it is and what kind. So if I take a look here, I see a vertical asymptote. That is called an infinite discontinuity. It's at x equals 3. That's the only issue, which means the graph is continuous everywhere else, which would be from negative infinity to 3, and then from 3 to infinity. Here in the next example, all there is a sad, lonely little hole. So remember that a hole in the graph is called a removable discontinuity, and it's located at x equals -1. Because there are no other issues, you would say that it's continuous from -infinity to -1, and then from -1 to 0. How about this one here? If you take a look at it, that looks like a quartic polynomial to me. And again, as you remember a few slides ago, because this is a polynomial is always going to be continuous, which means that there are no discontinuities, which you could say or not say anything. And if there are no discontinuities, then you would say that the function was continuous from -infinity to infinity. And again, I like to abbreviate dis for discontinuity, C for continuous. Feel free to do that if you're into it. One last one here. Is it possible that you could have more than one type of discontinuity? Absolutely. So I take a look here. Because there is a hole in the graph at -2, I would say that there was a removable discontinuity at x equals -2. That's the hole. Then notice here, there's a break where I'd have to jump from one piece to the other. So there is a jump discontinuity at x equals -1. No matter what kind of discontinuity there is, you have to incorporate it when you tell me where is the function continuous. So the function is continuous from -infinity to the first break, which is -2. Then from the first break to the second break, which is from -2 to -1, and then ultimately from -1 to infinity. So tell me where the discontinuity is, tell me what kind it is, removable, jump, or infinite, and then tell me where it's continuous, which is basically everywhere that there is not a discontinuity. That idea of being continuous is important for something called the intermediate value theorem, which I call the IVT for short. There's a couple different ways of explaining the intermediate value theory, and I'm going to show you a few of them. So here's what it says in its kind of formal definition. If A and B are real numbers such that A is less than B, we can see that because A is to the left of B, so long as f is a continuous function such that f of A does not equal f of B, which basically means that the y values at these two x's cannot be equal, then what the IVT tells us is that in the interval A to B, so between A and B, the function has to take on every y value between f of A and f of B. So I know that's kind of wordy. I know that there's a lot going on there. Basically, what it boils down to this. If the function is continuous, then by definition, there are no breaks. So considering a graph from the starting A to the starting B, and again, those are x values, so long as those values are not equal, and so long as their corresponding y values are not equal, because the function is continuous, you can say that every value between these two y values has to be defined. Here's another way of saying it, again, a little bit wordy. Let's say you have the curve of the function f of x. Let's say it's continuous on the interval. If you have some number w that is between the two y values, there must be at least one x value that has that y value as an answer. So both of these are telling you the same thing, but it's really up to you to pick the one that makes the most sense. Basically, again, it boils down to the fact that no y values are skipped between the starting y and the ending y because it's a continuous function. There's another interpretation of the intermediate value theorem which says this. If you have a polynomial and you evaluate it at two different x's, let's say a and b, if they have opposite signs, which means one of them is positive and one of them is negative, then there has to be at least one value, c, between them for which p of c equals 0, which basically means there has to be an x-intercept. Think about why that makes sense. So again, let's say you're starting off with the x value of a. Let's say that you get some negative y value. let's say you plug in some other x value b, and let's say you get some positive y value. If you're again taking into account the fact that the function is continuous, and we know that it is because it's a polynomial, the only way that you can get from this negative value to this positive value is by crossing the x-axis, which means an x-intercept has to exist somewhere between a and b. Of course, it doesn't have to always be from negative to positive. It could just as easily be from positive to negative. If you think again also about your graphing calculator, when you go to find the 0, which again is an x-intercept, it asks you for a left bound and a right bound. Sometimes when you go to do that, people will press enter and it'll say error, no sign change. When they say no sign change, the way your graphing calculator finds x-intercepts is by using the intermediate value theorem. It assumes that there are some values for which there's negative y's. Then if there's some y value that's positive, they know to look for x-intercepts between these two values, and that's how they're able to kind of quickly give you those answers. So here's an example. Show that the polynomial 3x cubed minus 10x plus 9 has a real 0 between -3 and 2. Again, this only works for real zeros, not for imaginaries. So if I'm telling you to show that there is a 0 between -3 and -2, again, a real 0, here's what you're going to do. You're going to plug -3 into the f function, and you're going to get an answer, -42. You're going to plug the second value into the f function. You're going to get a +5. So long as these two numbers, whatever they are, as long as they have opposite signs, then by definition, there has to be an x-intercept between -3 and -2. I could at some point ask you to find it. It would actually be very easy to find it if you use your graphing calculator, but try not to, because again, you might not always have it. This is just another example. So show that this quartic has a 0 between 1 and 2. So plug 1 into the function, get an answer. Plug 2 into the function, get an answer. So long as those have opposite signs, you can guarantee that there is a real 0 on that interval. And this is just showing you a graph. So somewhere between 1 and 2, there has to be some x-intercept. If that made sense to you, then I would suggest you pause and try it. So show that this equation has a root on the interval 1, 2. So pause and try it, then come back. All right, so if you've tried it, hopefully you plugged in 1. And if you plug a 1 in, you should get a y value of -3. Then hopefully you plugged a 2 in, you should get a value of 5. So because there is a sign change, we know for a fact that there is an x-intercept, a real x-intercept or a root. Remember, a root, a 0, an x-intercept, they all mean the same thing. There definitely has to be one between 1 and 2. And again, at some point, we could find it, but for now, we're just going to leave it there. Something else that we can kind of think about here is the fact that if you're talking about, we'll come back to that. So then finally, one last pause and try it. This is a multiple choice question. So if you're feeling confident that you know what you're supposed to do, go ahead and pause and try it and see if you can come up with the right answer. Okay, assuming you've tried it, you hopefully plugged in -2 and got -45. -1 gives you -19. Then 0 gives you -11. 1 gives you -3. And 2 gives you 23. The only one of those calculations that had a sign change was D, so you can say that there is in fact a root or a solution or an x-intercept between 1 and 2. So that's the end of lesson 14A. Again, I wanted you to go through it so you could kind of write things down and go at your own pace. Tomorrow we'll talk about lesson 14B together, and then you'll complete homework number 14 over the weekend. So thanks for tuning in, and we will catch you next time.